Okay, so this lecture is meant to walk you through the idea of something called torque. So torque is when a force causes a rotation. So far, anytime we've exerted a force on an object, we've caused it to translate. We've caused it to move in like a linear direction. Or even in this idea of like, if I throw something, like I've given it a force in a direction and it's translating. Torque is this idea of it's rotating. So I'm not just like lifting something up, I'm rotating something around a pivot. So it's when a force causes a rotation and it causes the object to rotate around a pivot point. So there has to be these certain conditions available in order for the torque to be exerted. Sometimes when you push something, it can't rotate. But there are other times when you push something and because it's constrained at a certain point, the object rotates, it pivots. The symbol that we are going to utilize for torque, we can't use T because that is too closely associated with tension. So we're going to use the Greek letter T. It's a Greek letter tau. Kind of looks like a pie, the symbol pi, but with only like one leg. And the equation for this is that torque is equal to FR sine of theta. So let me kind of give an overview of what all these things are. So let's say that I have something that can pivot right here. So I've got like a board and it's like connected to like a nail or something, and this thing can like swing up and down. Okay? If I were to push with a force this way, it would cause it to rotate around, okay? So by the fact that I'm exerting this force on something that can rotate, it causes there to be a torque in the situation, okay? So F is clearly this F value. This distance here is R. So F is the force applied. And R is the distance between the force, like where it's applied, and the pivot point. So distance between applied force and pivot point. Sometimes it's called the lever arm. Okay, so I'm going to just put that in a note. It's also called the lever arm. And then theta is going to be the angle between the applied force and the lever arm. So in this example, my theta would be here. The theta would be 90, okay? And so if you look at the equation to maximize your torque, you can have like a really big force value and get a big torque. You can have a really big R value, you get a really big torque. And then how do you maximize this sine theta term? Well, you should know from math that sine theta is bound between a positive 1 and a negative 1 in terms of its graph. And so the way you can make this to be a value of 1 is if theta is 90. So if you apply the force perpendicular to the lever arm, you will maximize the torque value. And I will kind of conceptually model that when we get into class, just with the idea of opening a door. So symbol is tau. Equation is tau, or torque, is equal to FR sine theta. Units, the units of this, it's a compound unit. So the units of force are newtons, and the units of distance are meters. So it's Newton meters, and typically they put a little dot there to indicate that you know it's like two separate things, so it's Newton meters. And then the angle doesn't have a degree, or it has a degree, but we don't have to put it in units. Okay, so that's kind of like the definition of torque, but something we have to kind of understand is that we no longer have like things moving right and left and up and down. Torque causes rotation. And so because it causes rotation, we have to kind of define what is positive rotation and what is negative rotation. So because torque causes objects to rotate, here is the definition, and this is what it is. It's this idea that counterclockwise rotation is positive. And sometimes you'll see me refer to this as counterclockwise. And then the opposite is true, and that is clockwise rotation is negative. And you'll see me refer to that sometimes as clockwise. And this actually comes from math, so blame the mathematicians. If we think about like this is 0 degrees, and then this is 90 degrees, and this is 180 degrees, mathematicians, like when they increase their angle, or the angle becomes more positive, it goes in a counterclockwise direction. So that is why counterclockwise is considered the positive direction. In terms of like how do we problem solve, very similar to forces in that we're gonna start with doing a diagram, then we're gonna look at net torques. Okay, so very similar problem solving. We are going to draw a diagram. We have to add on something here though too. We need to choose a potential pivot point. So where is this object? How could it potentially pivot? And our torques would be drawn from there. Okay? So we are going to include both forces and potential torques. And if an object is in equilibrium, we now have a couple things that have to be satisfied. So if an object is in equilibrium, we will now want to kind of think about, well, what are the net forces I have on my object, and now also what are the net torques I have on my object. Okay. So let's just look at the one example that is in your workbook and look at what happens with our torques and rotation. So this is the example you have. I think there's some words associated with your workbook. But essentially you have this situation where you have this object and it has the ability to pivot at point A. It may not have copied very clear, but that point A is kind of 1/3 of the way over. And you have these two forces that are acting on your, we'll call it a board. And if we think about this, like right now, this is just like forces, right? I want to show kind of torques, like how will this thing rotate? So when we're thinking about potential rotation, you're looking at, okay, this force being exerted on the object right there, like how would this thing rotate if that force was pushing it down? You can kind of visualize, let me get a ruler real quickly. You can kind of visualize, like, if it's pivoted there, I mean, it's being held there, and this force were pushing on it, you kind of say, like, how this thing would rotate. Like, pushing like this would cause a rotation, like, in this direction. So, like, that would be torque 1. It's caused by force 1. We're going to call it torque 1. And then on the other side, again, if I held this here, like that's where it has a potential to pivot. If force 2 were pushing on it, like this, you can kind of see how this thing would rotate in this direction. So that would be like my torque 2. So we can see that torque 1, or this force 1 is causing torque 1, which is a counterclockwise rotation. And force 2 is causing a torque 2, which is a clockwise rotation. So if I'm trying to figure out what the net torque on this thing is, the net torque on my system Remember, counterclockwise torques are positive, clockwise torques are negative. So you'd say, well, torque 1 minus torque 2 is equal to, I don't know, that's what I'm trying to find. What is my net torque on my system? Okay. So let's remind ourselves, general equation for torque is torque is equal to Fr sine of theta. So if I kind of apply that here, I'd say, okay, well, my net torque 1 minus torque 2 is equal to, I don't know, I'm trying to find that. This would become F1 R1 sine theta 1 minus F2 R2 sine theta 2. And I'm trying to find what the sum is. And so this is just a matter of like plug and check. Like you have all these force values, you have the R values, you have the theta values, just calculate. You do need to be in degree mode when you do your calculation. So go for it, calculate it out, see what you get, plug your numbers in, and what is the net torque in this situation. When you get back in class, we will talk about it and talk about its direction.